Hi there. Today we're going to look at something kind of fun, some early computational methods. One of these methods I referenced in a previous video, duplication and mediation. And then today we're going to see how it's done. So we're going to look at, basically we're just going to look at multiplying and how it was carried out by some previous people. It's not going to look exactly the same as what you're used to, what you learned in school. Although I've been seeing some memes and some other things floating around that apparently students in schools are learning some other ways, or people are like, why weren't we taught it this way in school? Or they'll attribute something to being, something they're doing in Japan. But really, some of these methods that I'm seeing in these memes are variations of what we're going to do today in this video. And then some of these methods were around a long time ago, before now. Okay, so that first one, duplication and mediation, it also used to be called peasant multiplication because of its origins, but it involves finding products by doing these steps. You write the two numbers next to each other. On the left side, you divide them in half, so that's the mediation part. And then if it's like a decimal, like 0.5, just drop that part and just keep the integer part. And then the right side is the duplication part, where you do the doubling. So it's also called halving and doubling. So for each number that you have on the left, double the number on the right until you get down to a 1 on the left side. Any rows that have even numbers on the left, you're going to ignore. And then whatever is remaining, add up the numbers on the right. And that will give you your desired result, believe it or not. Okay, for example, let's say that you want to multiply 17 times 26. Okay, so let's put 17 in a column. Let's put 26 in a column. Left side, you're going to cut it in half. Well, 17 divided by 2 is 8.5, but you're going to drop the 0.5 and just put 8. Then you're going to double the right side, halving and doubling. So it should be mediation and duplication, but whatever. 26 doubled is 52. Okay, then half of 8 is 4. 52 doubled is 104. Half of 4 is 2. 104 doubled is 208. Half of 2 is 1. 208 doubled is 416. All right, then we're going to go through, now that we're down to a 1 there on the left-hand side, and we're going to ignore all of the rows that have an even number there on the left-hand side. So the row that has the 8 on the left side, we're going to ignore, the 4, and the 2. Then whatever is remaining on the right side, we're going to add those up. 26 plus 416. And you get 442. So this equals 442. And there you go. If you want to, you might be looking at it and going, nah, I'm not so sure about that. Pull out your handy calculator, which is what I'm doing right now. You won't see it on the screen, but you can hear me probably. 17 times 26 equals 442. Woo! It's the same answer as my trusty TI-30X8 calculator that I have here on my desk. Now, the really cool thing is that it is multiplication. So multiplication is commutative, which means you can do it in any order and get the same answer. So if you'd put the 26 first and the 17 second, you'll still get the correct result. Might have longer columns, but ultimately your answer will be the same. So if you did half of 26, you'd get 13. Double 17, you get 34. Half of 13 is 6.5, so we'll put 6. Double 34 and get 68. Half of 6 is 3. Double 68 and get 136. Half of 3 is 1.5 or 1. Double 36, 12, 7, 272. All right, so we're down to 1. So let's cross out the left-hand side where we see even numbers. And then that leaves us with 34 plus 136 plus 272. And once again, we get 442 as our answer, because we wanted to add 34, 136, and 272 together. Yeah, so whatever, you look on the left, whatever's even, cross out that row. Then look on the right, whatever's remaining, add those up. Pretty cool, huh? All right. So that's your duplication and mediation. Let's do one more, and then we'll go talk about that a little bit further. Let's do 138 times 41. So I'll make two columns, 138, 41. Half of 138 is 69. 41 doubled is 82. Half of 69 is 34.5, but we dropped the 0.5 and just put 34. 82 doubled is 164. Half of 34 is 17. 164 doubled is 328. Half of 17 is 8.5, so we'll drop the 0.5 and go with 8. Double over here, we get 656. Half of 8 is 4. 656 doubled. 1312. Half of 4 is 2. 1312 doubled is 2624. Half of 2 is 1. Double over here. 5248. Okay. So cross out the left side where you see evens. Then go back and add up what's remaining on the right side. The 82, the 328, and the 5,248. Add those up. Okay, so I got 5,658. I keep double checking stuff because I'm like, hopefully I didn't make any kind of errors in my head there. Because I don't have you guys to start murmuring to alert me that something's wrong. But yeah, just put it in my trusty calculator, 5,658. So I didn't make any errors when I was adding there. And there we go. So, and again, if you wanted to switch it, if you wanted to put 41 on the left and 138 on the right, you'd probably get there faster because you're having a smaller number, but you'd get the same result in the end. So yeah, duplication means doubling, mediation means halving. We had briefly mentioned this back when we were looking at the Egyptian hieroglyphics. They didn't have the time or want to spend the effort to memorize multiplication tables. So this method works pretty well. Halving and doubling or something you could easily do even with objects like pebbles or something. You don't have to know like these multiplication tables off the top of your head. Still certain parts of Russia that use it. And then I think it might still be called peasant multiplication based on that. If you'd like to get into the nitty-gritty of how it works, like a mathematical proof, I have a link there to Dr. Math at the Math Forum. I'm not going to get into how it works, but it does, and you can read that at your leisure if you'd like. Okay, another method, the galley method. It's called this because it looks like if you took a ship and chopped it in half, you would be using that cross section of the ship's galley that's what it looks like when you're doing this method. So again, we're focusing on multiplication. We're going to draw a box. We're going to have one of the numbers written across the top of the box and the other number written down the right side of the box. And we're going to draw columns and rows, so it's going to look like a spreadsheet kind of thing. And in each little cell, we're going to put the results if you had multiplied the numbers that match up for that row and that column. You're going to end up adding diagonals, and when you're done adding the diagonals, the final result is the product. Now, it's a lot of words, hard to imagine what the heck I am talking about. So let's say that you wanted to multiply 5 times 417. Let's say that was something you needed to do, and you wanted to use the galley method. I mean, you could put it in your calculator right now, and you say, oh, 5 times 417, oops, I just mistyped that. 5 times 417 equals 10,425. But, yeah, you want to be kind of fun and do something else. So one way you could do this is draw a box. Let's put 417 across the top. And let's put 5 on the right side. And let's draw some cells. So since 417 is 3 digits, we have 3 columns. Since 5 is 1 digit, we have 1 row. And I'm going to switch colors to fill in the boxes. We're going to draw little diagonals in each little square, each cell. First cell, we have a 4 and a 5. We have column is 4, row is 5. 4 times 5 is 20. So we're going to go ahead and write 20 in there. Second cell, column is 1, row is 5. 1 times 5 is 5. So we're going to write 5 in there. Third cell, we have column is 7, row is 5. 7 times 5 is 35. So we're going to write 35 in there. Five times 417. Well, in my calculator, I get 2,085. I'm not sure. Did I say something else earlier? This calculator's crazy. Okay, so I should end up with 2,085 when I'm done with this method. But what I'm going to do is I'm going to add the diagonals. Let's use pink. I'm going to look along the diagonals and add each one up. If I end up with the double digits, then I'll do the carrying process to the next diagonal. So the far right, first diagonal, I have a 5. And then I'm going to make my way to the left. The next diagonal, I have 3 plus 5, which is 8. Next diagonal, 0 plus 0 is 0. Final diagonal is a 2. So 2,085 is my result. And if I put it in my calculator, I did 5 times 417, and I got 2,085 in my calculator. Pretty cool, huh? Now again, multiplication, the order doesn't matter. So let's say you put the 5 across the top and the 417 down the side there. So basically it's just rotated. Okay, so my diagonals. 5 times 4 is 20 for that first cell. 5 times 1 is 5 for that second cell. And 5 times 7 is 35 for that third cell. I'm going to start down here. That's a 5. And I go like this. 5 plus 3 is 8. 0 plus 0 is 0. And then 2. So once again, I get 2,085. Same result. Multiplication is commutative. The order does not matter. Okay, let's do an example with a few more digits than that. Let's do 47 times 259. If I put in my trusty calculator, I know I should get 12,173. But let's do it with this galley method and see what happens. Let's put, I like putting the longer number across the top. I just feel more comfortable doing that. You don't have to, but I like doing that. But you can do it the other way. You can do 47 across the top, 259 down the side. Totally up to you. But I'm going to have a column for 2, a column for 5, a column for 9. I'm going to have a row for 4 and a row for 7. Let's draw the diagonals. All right. The 2 times 4 is 8. So this cell here, upper left cell is going to have an 8, 0, 8. 5 times 4 is 20. So put a 20 here. 9 times 4 is 36. Let's put 36 there. Then for the next row, 2 times 7 is 14. 5 times 7 is 35. 9 times 7 is 63. Okay, so starting with this bottom right, we're going to start adding up the diagonals. like that. Okay, so first diagonal is not really anything to add, so you get a 3. Next diagonal has 6 plus 6 plus 5, which is 17. But just like in a normal addition problem or multiplication problem, we're going to write the 7 and carry the 1 over here. 1 plus 3 plus 0 plus 3 plus 4, that's 11. So we're going to write a 1, carry the 1. 1 plus 2 plus 8 plus 1 is 12. So we're going to write a 2, carry the 1. 1 plus 0 is 1. So these numbers here make up your answer, 12,173. Pretty cool, huh? All right, let's do a really big one. Let's do 634 times 832. So 634. Again, you could put 634 across the top, or you could put 832 across the top. Doesn't matter. Boxes will look different, but final results will come out the same. Okay, so column for 6, column for 3, column for 4, row for 8, row for 3, row for 2. Switch to my blue to make up my little diagonals here. Six times 8 is 48. 3 times 8 is 24. 4 times 8 is 32. 6 times 3 is 18. 3 times 3 is 9. 4 times 3 is 12. 6 times 2 is 12. 3 times 2 is 6. 4 times 2 is 8. Okay, so my diagonals. This one's an 8. 2 plus 0 plus 6 is 8. 2 plus 1 plus 9 plus 0 plus 2 is 14. So I will put a 4, carry the 1. 1 plus 3 plus 4 plus 0 plus 8 plus 1 is 17. So I'll put a 7, carry the 1. 1 plus 2 plus 8 plus 1 is 12. Put a 2, carry the 1. 1 plus 4 is 5. So these pink numbers make up my answer, 527,488. And if you go ahead and put it in your trusty calculator, 634 times 832, voila, same answer, 527,488. So a little bit of background on this method. It was popular in India before the fall of Rome. There was a mathematical history is funny. History is funny this way in that it's so spotty, and the world was so big at one time to people. There was a time when different countries didn't know others existed, and so you have this development in like mathematical history that occurred over in China, occurred in India, occurred in these different areas. And then even within Europe, different countries had people developing things individually, but often simultaneously without awareness that somebody else was doing the same thing. So like for example, in calculus, the invention of calculus, you have both Isaac Newton and you have Leibniz. They both invented calculus, but they each had their own notation. So it's like if you end up taking a calculus class if you're doing something called a derivative, some classes will use Newton's type notation, other classes will use Leibniz's. It just depends on what class you're in, and who the professor, and whether it's a physics-based class or or pure math or whatever. But anyways, so this method was already popular in India before even the Roman Empire fell. They would often have a board, probably with a little galley thing already painted on there, and then they could sprinkle sand or flour on it and then scratch in the numbers to write. And that was something, any peasant could carry around a board, anybody. And traders, if you were going like to the market to trade things, to barter, whatever, you could carry a board pretty easily, and then you could get down on the ground, sprinkle some sand or flour on it, scratch your figures, and then when you're done, smooth it out and start over, or dump the sand off and walk away. So it's sometimes called the scratch method, but also became the galley method from it looking like the galley of a boat, like if you took a boat and chopped it in half, looking at the galley from the side there. That's kind of a similar shape, similar with the rectangles and the little diagonals through them. The method was introduced to Europe in the 13th century by a man named Fibonacci, and is now called lattice multiplication. So you might have seen, I've had people tell me that their kids or themselves, they themselves learned lattice multiplication in school. So you never know. You might find it pops up in your life pretty soon. And Fibonacci is somebody that you will see again in the near future. Start taking note of him for your mathematician list, because we do talk about him some more. All right, another person to take note of your mathematician list, John Napier. And why am I bringing this guy up? Well, he invented something called Napier's rods, or Napier's bones, and these look very similar to the galley method when you use them. So John Napier, add him to your list. English mathematician who invented many devices for performing calculations quickly, including not only Napier rods, but also some simple calculating machines. And if any of you have taken Algebra 2 in high school or college algebra here at the college, you've learned about logarithms. It's not a music thing. It's not like logarithms and blues or something. No, logarithms are another way of working with exponents. They're another way of writing exponents. But John Napier, you can thank him for developing the theory of those. But anyways, what does this look like? Well, this tool, scroll down a little further, the tool looks like these long strips. It can be sticks or bones with the values etched into them. And then when you really look closely at how you use them, it looks like the galley method. But the students in Britain were using these until the 1960s to learn multiplication. If you do a search for Napier's bones or Napier's rods, the images will show like these nice carved bones or rods, or wooden sticks, those kinds of things that they could carry around in a pouch. The students could. They could pull them out and use them. But you line up the rods for the digits in one of the numbers that you're trying to multiply next to something called the index rod, which in this example, the one rod is the index rod. Usually it doesn't say one though. Usually it says like index or something. You use the galley method to find the product of those digits. And if you need to, you can multiply the result by a power of 10. But you repeat until all the digits have been multiplied together. Add the results. Okay, in this example, I pulled this from the Wikimedia Commons, so it's a free image out there to use. So I'm going to just use the example they have on there. But they are interested in multiplying 384 times 6. So what they've done is they've used the index rod here. And they're focusing in on the 6. Actually, let me see about using the highlighter. So they're focusing in on the 6. And then notice that they've taken the 3, 8, and 4 rods and lined those up for the 384. And then right next to the 6, they have the numbers they want to use. But this is really like the galley method. Because if you write this out like you would in the galley method, it's like you have 3, 8, 4 times 6. But the nice thing about having these little rods is you don't have to write it out because it's already there for you. They've already got the little multiplications in there. They've got the fact that 3 times 6 is 18 in there. They've got 8 times 6 is 48. 4 times 6 is 24. So all that leaves you to do is to add up the diagonals, just like you do in the galley method. And so you get the 2,304. And that's it. That's the process. Now, if you were multiplying by something bigger, like let's say you were doing 384 times 26. Well, you would look at the 384 times 6, and you get that. That's the 2,304. And you look at the 384 times 20. Well, first do 384 times 2. So you can go up there and you can, I can't select a different color for my highlighter, but let me maybe use green. And you can go up to the 2. And you can focus in on that row. Well, 384 times 2, if you start adding up the diagonals up there, the blanks are zeros. I've been writing in zeros when I do this, but the blanks are zeros. So you start adding up your diagonals, you get 8, 6, 7. So you get 384 times 2 is 768. But in 26, 2 is in the tens place. So to do 384 times 20, just add a 0. And then you add up those results. You add up the 7,680 with the 2,304 from earlier, and you get 9,984. So put that in your trusty calculator, 384 times 26, and you get 9,984. You get the same result. All right, let me show you how this lines up with what you know for your traditional multiplication. Let me do a little thing off to the side here. Like if you have 384 times 26 normally, like what you probably learned in school was 6 times 4 is 24, carry the 2, 6 times 8 is 48, plus 2 is 50, carry the 5, 6 times 3 is 18, plus 5 is 23. So notice there's the 2,304 that we have right here. Then usually you put a 0 here, or an x, before you start multiplying the 2. 2 times 4 is 8, 2 times 8 is 16, carry the 1, 2 times 3 is 6, plus 1 is 7. Well, there's the 7,680 that we had here. And then you add them up just like we did. So this method's not a far stretch from what you're used to. It's just a different way of laying things out. And it's kind of, with using the Napier's rods, it's like a really quick way of having like half the work done for you so that you don't have to write it all out and do all the carrying and everything like that. But there you go. So that's another method. Okay. Now the very last thing that I throw on here, it's not in your book, but I always think this is interesting. There's something called Vedic math. It's an ancient system from India. It had been kind of put aside for a long time, and then it was rediscovered somewhere between 1911 and 1918. And the system has 16 formulae, which are written in words. And for them, mathematics is derived from these 16 formulae. The methods simplify problems so that many things can be done mentally. So it's kind of fun to explore. Not a big, go do that on your own time, have some fun, not going to be on your test or anything. I just wanted to share that because that is another system of how some mathematics can be done. And you might be able to wow and amaze your family and friends with it, because it really does, like that website does a pretty good job of breaking down how you can do certain things mentally. So you can get really fast at certain computations and not have to use a calculator. But I'm not going to go to that link right now. I'll let you do that. But enjoy. Thank you for joining us. And that is it for now. That actually wraps up this unit. So when I see you again, we'll be in a new unit. Take care.